So Archimedes principle. Let me just give you a brief overview of what it is. If someone is on land, usually they're really difficult to lift up. But if they're in a swimming pool or they're in the ocean, like you're at the beach, like Maracas Beach or whatnot, and you try to lift them up while they are in the water, they seem what? Lighter. How much of you all can confirm that? Like you try to lift someone in water and they actually seem easier to lift. Let's clarify that case. Great. So let's do the maths behind it. And the guy who figured out the maths behind it, obviously his name was Archimedes. So the first thing they're going to probably ask you in the exam, just for one measly mark, is the definition of Archimedes' principle. Take down the definition. Forget if you understand the definition or not. By the time we do all the calculations today, you're going to understand all of those fancy words in front of you. Right? So take a 20 seconds, take down the definition, and we're going to continue. Wow. All right, so let's look the two formulas we're going to be using over and over for Archimedes' principle, right? Is the two formulas over here, which is two very basic formulas. One is how you convert mass into a weight. Remember, weight is a force, and weight is the one that's being measured in newtons. And weight, how it's a force, it must have a direction, which will always be downwards, right? So that's a quick reminder, right? The weight has to be measured in newtons, the mass is in kilograms, and well, gravity is meters per second squared. And I'm sure you all are very familiar with the second formula, right? Density is mass divided by volume. All right, so to explain why something feels lighter in a liquid, what we're going to do, we're going to take a piece of metal. The material really isn't too important, right? I want you all to do me a quick favor. For this piece of metal over here, I want you all to calculate the weight, not the mass. I want the weight of the object. Right? So you're going to need your calculators today for sure. You're going to take it very slow today. All right, so let's see. For the piece of metal, you were given the density and you were given the volume. So how do you calculate mass? The first thing we have to do is calculate the mass. And once we get the mass, we're going to convert it to what? Weight. So to calculate the mass, you notice the density was given in kilograms per meter cube and the volume was given in meter cube. So there were no tricks in this question. So the density is 3,500, right? And the volume is how much? The volume is 0.02. So to calculate the mass, we take the density and multiply by the volume. And to me, when we multiply that, we got 70, but this is mass. So it's kilograms. But I want the weight. The weight now is the mass multiplied by gravity. So we have the mass, which is 70, and gravity is 10. So that means the weight is how much? 700 newtons. Now, when you're putting that on the diagram, you just can't write 700 newtons. Weight is a force, so it's very important in the CXC exam, you put the arrow as well. So it's 700 newtons downwards, right? So for the persons who got it wrong, well, I hope you see your mistake now. So let's on land, right? The weight of the metal block is 700 newtons. Now, 700 newtons is pretty heavy. If you try to lift that up, it will give an average human being a lot of pressure to lift, right? It's pretty difficult. However, if we take this now and put it in a container of water, now we are going to assume it's pure water. And the density of pure water, right? The examiner will give you it in the exam anyway, right? So the density, I'll put W here for water, is 1,000 kilograms per meter cubed. Does everyone agree that if I put this in the water will rise because the metal is going to displace some of the water? I think we could all agree with that. Who can tell me how much water will be displaced? How much water will be pushed aside to make space for the piece of metal? Think on it, right? Okay. All right. So tell me something, right? The volume of the piece of metal is 0.02. So that means when you put it inside here, it's going to push aside the same volume of water. Does that make sense? If the volume of this is 0.02, then it will push aside the same volume of water to make space. So that means the volume of water pushed aside is also 0.02 meters cubed, right? You have to displace the same amount of water. Like if you jump, like if you have a certain volume and you jump into a swimming pool, you are going to displace or push aside the amount of water equal to your volume, and volume is how much space you occupied. Okay, right? So and the people who are getting it wrong are like, oh, okay, you understand now. Great. All right, so remember, this volume of water that has been pushed aside, the water itself will have a mass. And of course, anything with a mass is going to have a weight. So check this out. To calculate the mass of water pushed aside, to calculate mass, we take the density of the water, which is 1,000, and we multiply by the volume of the displaced water, which is 0.02. And of course, well, for some strange reason, I need my calculator for this. Right, so we have 20 kilograms. Right, so the mass of water displaced is 20 kilograms. So what is the weight of the water displaced? Well, it's 20 by 10, right? That's how you convert mass to weight, which is 200 newtons. Right, so here what Archimedes was saying, right? This is what the definition is basically saying. On land, right, the weight of the iron object here is 700 newtons downwards. But when you place it in the liquid, water in this case, it displaces a certain amount of liquid, and the weight of that liquid from calculations is 200. What he is saying is that this weight acts upwards. So it's 200 newtons acting upwards. And he has called this upward force an upthrust. I think I spelled it wrong, but we'll clarify that just now, right? So what do you all know about forces in the opposite direction? Do you add or do you subtract? What do you all think? You subtract. So that means at the end of the day, if 700 is acting downwards and 200 is acting upwards, the resultant is how much? 500 acting downwards. Which means on land, if you are trying to lift it, its apparent weight is 700 newtons. But when you put it in a liquid, its apparent weight is only 500 newtons. Hence, to lift it up in the water, it's going to be easier. All right? So I know some of you all are probably need more than one examples to understand this carefully, right? Okay, so this here is the resultant force, which is 700 minus 200. So this is the resultant force. Let me know when you take down everything on the screen. Do not be worried if it didn't make 100% sense as yet. I have plenty more examples for you, right? So let me know when you're finished, please. All right. So what made this question so easy? This is considered to be an easy question in the exam. Is because there were literally no tricks. What do I mean by no tricks? You notice that the examiner gave you the volume. He came straight out and told you what's the volume of the object. Also, you notice it's in meters cubed and the density was given in kilograms per meter cube. So you didn't really have to convert one unit to a next unit. Look what's going on with the next question, right? Right, so I have the same thing twice. But before, sorry, the trick and starters here, sorry. Look what's going on here now. We're going to take the same metal block and we're going to put it in the water. But look at the difference. In the first question, the whole object was submerged. Now, only half the object is submerged, right? Now, the examiner has to tell you the fraction that is submerged. So I come like the examiner. Tell me something. Will the same amount of liquid be displaced if only half the amount is submerged? No, right? Correct. So who can tell me how much water will be displaced? What's the volume of the displaced water? And we assume it's the same water with the same density, 1,000 kilograms per meter cube. Rashawn, correct. Right, Christian, Ariana, Avidesh, wrong, right? Remember, if the full object is 0.02 and only half the object is submerged, then the volume is 0.01 meters cubed. Can you all calculate the apparent weight? In this case, I do back all the calculations, right? Don't use the common sense method. I know some of you are will use a common sense method. But as practice, I want you to do back all the calculations to show that what would be the final weight or force on the half submerged piece of metal. And when you're finished, send the answer. Let's see. First of all, well, let's just recalculate the mass of the metal, right? Mass is what? Density by volume. The mass of the metal is its density, which is 3,500, and its volume is 0.02. So this gives you what? 70 kilograms. To convert it to weight, we multiplied by gravity, which is 700 newtons. So that means the weight is 700 newtons, just like in the previous example. Now, less water is going to be displaced because it's only half immersed. So let's calculate the mass of that displaced water. The volume of water is now what? 0.0, sorry, the density of the water is 1,000 and its volume is what? 0.01, half this, because only half is immersed. So I think when we multiply this, we're going to get 10 kilograms. But that's mass. We need it as a weight. So we take the 10 kilograms and multiply by gravity. Mass by gravity will give us the weight. And you're going to get 100 newtons. Once again, Archimedes was trying to say, the weight of that displaced water, it's an upthrust force and it acts upwards. So 700 is downwards, 100 is upwards. Those forces are in opposite directions. Hence, the resultant force is 600 newtons, which is still lighter than when it's on land. Remember, when it's on land, it's 700 newtons, but when it's in the water now, it's 600 newtons, so it's lighter. All right, so I'm just leaving that on the screen just for a few seconds. All right, so look at this question now. They give you a piece of metal now, but the examiner wasn't nice enough to give you the volume straight out. And there's another trick here. Look at this carefully. The density is given in kilograms per meter cube. So that means this density, right? Density and volume related. For this to work out, the volume has to be in meters cube. You notice I give you all the lengths in centimeters. You think you all could calculate the volume of that block for me, but I want it in meters cube. There's an easy way to do it, and there's a hard way to do it. You choose any method. All right, so remember, we only concentrating on the volume. Now, don't think of this as a physics question as yet. Think of it as a regular boring maths question. What I would do in the exam, right? We know the volume is length by breadth by height. So what I would do if I want my volume to come out in meters cubed, well, guess what I'll do? I'll divide each length individually by 100. So that way I'll get it in meters one time. Because the mistake some of you all are making, you're multiplying the 40 by the 5 by the 20, and you're not too sure how to convert centimeters cube, which is different from centimeters, into meters cube. You're not sure if they divided by the final answer by 100, by 1,000, by 10,000, or 1,000,000. So take the easy way out. Divide all the sides by 100 first, right? So 40 divided by 100 is 0.4. 5 divided by 100 is 0.05. 20 divided by 100 is 0.2. So now we just say length by breadth by height, 0.4 by 0.05 by 0.2. That's the easy way out, well, in my opinion. And this is what you're supposed to get, guys, for the volume. If you get anything else other than this, it's wrong. 0.004 meters cubed. And notice some of you all put it in standard form. So if you put it in standard form, it's 4 multiplied by 10 to the power minus 3 meters cubed. Right? Let's just stick with this one. For those who got it wrong, you understand the mistake? Right? And remember, these types of questions will come in normal maths as well. Normal maths. All right. So you think you all could calculate the weight of the block for me? It hasn't gone in the waters yet. I want the weight of the block, which means the answer has to be in newtons. Wait for those answers to come up. All right, so the first thing we have to do is calculate the mass before we calculate the weight. So mass is what? Density by volume. We have the density is 2,400 and the volume we now calculated. So we multiply them and we get 9.6 kilograms. But that's the mass. I want the weight. So then we have to multiply by gravity and we get 96 newtons. So the downwards, where the weight of this object is 96 newtons. The whole thing is submerged in water now. So some of the water will be displaced. Now, since the whole thing is submerged, the volume of water displaced is also 0.04 meters cubed. And we're going to assume it's pure water again. So let's assume that the density of the water is 1,000 kilograms per meter cubed. I want you all to calculate the upthrust force for me. Here. So the first step is to calculate the mass of water displaced, right? So the calculate mass is density by volume. The density of the water is 1,000. The volume is 0.004 because the whole thing is submerged. When you multiply this, you're going to get 4 kilograms. The mass is 4 kilograms. But we need the weight of that water. So what we have to do now is take the 4 and multiply it by gravity. And quite a few people forgot to multiply it by the 10. Now, obviously, we're going to get 40. And what Archimedes was saying is that 40 newtons, because weight is a measurement of force, it's a type of force, sorry, is going to act upwards. So now what would be the resultant force? Well, it is minus both of them, and we're going to get 56 newtons, right? So when it's in the water and you're trying to lift it up, you're only going to have to try to lift 56 newtons rather than 96 newtons. Right, so take down what you need to, and we're moving on to our next question. All right, so move down here now. All right, so here we have a little more interesting example. A beach ball, right? If we take a beach ball and push it down in the water and let it go, could we all agree that it would just shoot back up? Like it would just spring out of the water? Right. We're going to do the maths behind that now. We're going to try to figure out why it springs back out. Right? But let's just change up the question and make it a little more interesting. You know, in the past examples, we were using what? Plain water. Let's say we have a purple liquid, right? And the density of this purple liquid here, let's say it's 1050 kilograms per meter cube, right? So it's a little different from water. Let's pretend the water is Kool-Aid. I don't know if you all know what Kool-Aid is, right? It's a type of drink or whatnot. So here's what I need to know, right? These values here, by the way, represent the beach ball. If the beach ball was on land, right? It's not in the water as yet. Could you all calculate the weight for me quickly? Just calculate the weight. I don't think it have any tricks in it. All right, so the first thing we're going to do is calculate the mass of the ball. So the density of the ball, or whatever it is it's 4, and its volume is 0.8. So if you multiply it, you're going to get 3.2 kilograms. And of course, I think we know how to convert it to weight by now, right? 3.2 by gravity, mass by gravity, you're going to get 32 newtons. So the downward force, right? The weight is 32 newtons. Now, I want you all to calculate the upthrust force for me. What would be the upthrust force? And you know, you're going to realize something. When you calculate the upthrust force, it's going to be different. The whole situation is going to be different from the previous 2 examples. All right, so let's see what mistakes are being made here. Now, the only way this beach ball, right? So, well, let's do the calculation for first, Jordan, right? I have to show you why, right? So the only way this beach ball is going to be completely submerged in the water is if you force it down, you know. You know, if you just throw a beach ball just so on the ocean, it's not going to sink on its own unless somebody applies a force. But anyway, let's calculate the amount, the upthrust force. So does everyone agree at least that if the ball is totally submerged, it will displace 0.8 meters of water? Because that's how much water will be pushed aside. It has to be equal to the volume of the ball. So let's calculate the mass there. The calculated mass is density by volume. Now it's liquid we're dealing with. So the mass will be the density of the liquid, which is 1050, multiplied by the volume of the liquid. Let's do this. Let's see how much we get. 1050 multiplied by 0.8. I'm getting 840 kilograms. But I need it as a weight, a force. So I multiplied by 10 and I got this. Now remember, this is the upthrust. Look at which one is greater now. The weight is only 32 and the 8400 is upwards. So this time the resultant force is not downwards. Look at the other examples. In the other ones, the downward force was always the greater one, right? So this time, the upward force, well, and you still have to minus it, right? So let's just minus it here quickly. And you minus the 32, we get an 8368, but not downwards, it's upwards. So that is why the ball moves upwards, because the resultant force itself is upwards, right? Yes, there was chemistry as normal on Friday. I don't recall canceling class. All right, so here's something now. We have an object, right? We're going to throw it, we're going to throw it in water. So you have the dimensions and whatnot of the object. Now the mass of the object is what? 2,500 kilograms. Sometimes when something is floating on the water, and all the times, right? Piece of the object, if something is floating, some of the object will be above the water and some of the object will be below the water. Let's call the piece below the water, this length here, only this portion. The whole thing is 4 meters, by the way. Let's call this distance X. And let's assume it's pure water, which is 100 what? Kilograms per meter cube. That's the density. I want you all to try to figure out how much of the object is below the water, provided that the object is floating at the moment. Take a try. You don't have to get it right. Just try your best to get it out. Now, if something is floating, that means the downward force has to be equal to the upward force, right? Because when something is floating, it's not moving up and it's not moving down. It's in total equilibrium. So if this block, right, let's say, if this was on land, what would be the downward force? Well, you don't have much calculations to do there because I gave you the mass of the block. So to calculate the weight of the block is this value multiplied by 10, which is 25,000 newtons, right? Now, for this to float, the upward force, because of due to explained by Archimedes' principle, how much would the upward force have to be for the whole situation to be in I'm using a fancy word here, equilibrium. Nikane correct, Rashawn correct, Jordan correct, right? So the upward force has to be 25,000 newtons as well. So what we're going to do, right? We're going to calculate the upward force. We will get an expression for it, and we're going to put it equal to Mr. 25,000. So we have to figure out how much water is displaced. The water displaced is only determined by the portion underneath the water, the submerged portion. So I'm using a little math skills here. Here would be 20 meters, right? Here's 20, here's 20, here's 20. We know here's X, right? And we know here is what? 2. So to find the volume of water displaced is length by breadth by height. 2 by 20 by x, which will give us 40 x meters cubed. Everybody with me so far? The volume underneath the water, the submerged portion, is 40x meters cubed. Now, water is going to be pushed aside, and the volume of water pushed aside is going to be equal to this. Now, that water being pushed aside is going to have a weight. And of course, it's definitely going to have a mass. So let's calculate the mass first. Mass is density by volume. We have the volume. Let's multiply it by density. And we're going to get 40,000 kilograms of 40,000 x, sorry, right? Because it's 40x by 1,000. So this here is the mass. To calculate the weight, right? We have to multiply the mass by 10, which gives us what? 400,000 x. And we now said that this weight, which is acting upwards, has to be equal to this guy here. So the whole system is in equilibrium. So you have to take this upthrust force, which is 400,000, make sure I have enough zeros here, x is equal to 25,000. You think you all can calculate x for me now? There's a secret multiply, you know what to do, throw across the multiply, you get a divide. Tell me how much you get for x there. And this is what some people were sending me. X is 0.625, and the answer has to be in meters because x is what? A distance, a length.